The number of chocolate chips in a popular brand of cookie is normally distributed with a mean of 23 chocolate chips per cookie and a standard deviation of 1.7 chips. When the cookies come out of the oven, only the middle 90% in terms of the number of chocolate chips are acceptable. The rest are considered defective. What are the cutoff numbers for the number of chocolate chips in acceptable cookies? So, first thing that I notice is that we're working with a distribution that's normally distributed. And that's a great time to sketch out a bell-shaped curve and indicate the mean of the distribution and the standard deviation. All right, now, only the 90% and the center of the distribution are going to be accepted. Everything outside of that range is not accepted. So for instance, let's say this is the middle 90%, and I'll shade that in green because that's accepted. All right, so the middle 90% are accepted. Then we have this area and this area, which are not accepted. All right, now, when I have a mean of 23, that's right in the center of the distribution, and this is measuring the number of chocolate chips. So this axis is labeling a number of chocolate chips. So what I'm looking for here are two values. This lower x value I'll call x1, and this upper x value, which I'll call x2, which are separating the middle 90% from the extraneous values. But I need to know how many chocolate chips that is in order to make a distinction. So here's how we'll go about that. Since I want to find a value that's relative to the units of measure of the mean and standard deviation, I will use inverse norm. So for instance, x1 is going to be the inverse norm. An inverse norm in the calculator, of course, takes 3 inputs. The first input is always an area to the left. Then the second input is the mean and then the standard deviation. So area to the left. So the area to the left of x1, because x1's the value we're looking for first. So how much is down here in this red area? Well, there's 90% in the green area. And then the thing is, if I took 1 minus that, if I took 1 minus 0.9, that gives me 10% of the area in red. But there's 2 of these red regions. If the distribution is perfectly symmetric, and it's supposed to be, then that means we would have 5% of the area in each of these regions. So the area to the left of x1 is 5%, or 0.05. Then the mean of the distribution, of course, is 23, and the standard deviation is 1.7. So this lower bound of acceptance, if I hit second and vars, that will take me into the calculator and ring up the distributions menu. And I'm looking for inverse norm, which takes 3 inputs, and I've already decided what those inputs are, so I'm just going to type them in to get a result. So 20.2 is what I will use here. And of course you can't have 0.2 of a chocolate chip in there, but just using the accuracy of the mean and standard deviation, since the standard deviation is to 1 decimal. But of course follow any rounding rules that you've been given in the problem. And it's possible that some of you received a menu at that point when you did the inverse norm. Some of the later model calculators do that, and this is what it looks like. It's just trying to help you remember what the inputs are to each function. So the first one is your area to the left. The second one is the mean, and then the standard deviation. When you hit paste, all it does is places that information comma separated into the function, just as a helper, that's all. All right, now we also need to find the value of x2. To find it, again, we'll use inverse norm. But we need to give the amount of area to the left of x2. Well, to the left of x2, there is 90% here in green, plus an additional 5% down there in red, because both of those regions are to the left of x2. So 0.95 is the area to the left of that value. The mean is 23, and the standard deviation is 1.7. So, using the calculator, second in vars, down to inverse norm, 0.95, the mean and standard deviation are the same, and there we go, 25.8. And there are the boundaries of the middle 90%.